Modeling with differential equations. So the first thing we might ask is, what is a differential equation? For our purposes, a differential equation is an equation that contains an unknown function and some of its derivatives. Now, in this course, we will only be working with what we call the ordinary derivatives, what we've learned so far. Later courses will deal with something called partial derivatives. We will not see those in this course. You generally learn about partial derivatives in a Calculus 3 course, and then you can start studying what are, partial differential equations. We're only going to look at a few cases of what are called ordinary differential equations, or ODEs. So these are all examples of ordinary differential equations. For example, we have y prime is equal to 1 plus 7x minus 4y. That's an ordinary differential equation, where y, so when we see this notation, we have to understand that y is the dependent variable, and we're going to make the assumption that since we see x here, that x is the independent variable. Now, the order of a differential equation is the order of the highest derivative that occurs in the equation. So since I see a y prime, I would say that this is a first order differential equation. The second example, I have y double prime plus y prime plus 12y equals 0. So this again is an ordinary differential equation. I see the y prime. I don't see the independent variable. So I have a choice here. I can use any variable I want. But what I would normally say is, from here I see that y is the dependent variable, and we would either use x or t usually as the independent variable. I see y double prime, so this is called a second order differential equation. In the third example, dy dt is y to the fourth minus 6y cubed plus 8y squared. So dy dt, y is the dependent variable again, but since it's with respect to t, t is the independent variable. Looking at the order, this is a fourth order differential equation. And in this last example, we see x double dot plus 4x is equal to sine squared 2t. So this is another notation that's used to represent a derivative. So what this is saying is x is the dependent variable, and t is the independent variable. And x double dot is equivalent to x prime prime of t. Okay, so that's just another notation. We're not going to use that notation in the rest of this course, but I wanted to at least familiarize you with it. You will definitely see that notation in a true differential equations course. Again, this would be, since it's a double dot, this would be a second order differential equation. Okay, so that's just a little bit of the notation, a little bit of the naming of these things. Now let's kind of talk a little bit about how we use them in modeling and what do we mean by a solution. So we actually considered a differential equation a while ago in this course. I think it was in the very first unit that we studied. We saw this sort of statement, or something closely related to it. It said, suppose a population grows at a rate proportional to its size. So if I let P represent the population at time t. So P is a function of t. Suppose a population grows at a rate. Well, that's dp dt. The population grows at a rate, and the rate is proportional to its size. So then dp dt is equal to some number times the population. The rate of change of the population is proportional to the population. dp dt is equal to kp. This is a differential equation, and in fact it's a first order differential equation. So a function f is called a solution of a differential equation if the equation is satisfied when y equals f of x and its derivatives are substituted into the equation. So here's a claim based on the previous exercise. Claim any function of the form p equals a e to the kt is a solution of dp dt equals kp. So that's my claim. Now I need to verify this claim. So let's verify it. If p equals a e to the kt is a solution, then I should be able to substitute it and its derivatives into the differential equation and come up with a true statement. I should be able to satisfy it. All right, so if p is equal to a e to the kt, then dp dt would be equal to a e to the kt times k from the chain rule. All right, so so there's, in a sense, the left-hand side. So dp dt is equal to a e to the kt, and k times p would be equal to k times a e to the kt. And so therefore dp dt is in fact equal to kp for p equals a e to the kt, because both of those are equivalent, right? A e to the kt times k is equal to k times a e to the kt. So we verified that that is a solution. Show that every member of the family of functions y equals c e to the x squared over 2 is a solution of y prime equals xy. All right, well, if y is equal to c e to the x squared over 2, then y prime would equal c times e to the x squared over 2 times, from the chain rule, let's see, we would have a 2x over 2, which is just x. So y prime would be c x e to the x squared over 2. Now xy would be x times c e to the x squared over 2, which is also equivalent to c times x times e to the x squared over 2. So that checks out. So y prime equals xy for y equals c e to the x squared over 2. We've just verified that by substitutions and a little differentiation. But now we're asked a second exercise related. solve the initial value problem y prime is equal to xy and y of 0 is 5. So here we have a differential equation, and this is called an initial value. It's an initial value because it's when the independent variable is 0. And so we call that an initial value. All right, so we've said in the previous slide that y prime equals xy has solutions y equals c e to the x squared over 2. So now that c is some constant, right? It's some relic of generally of an integration process. So now we need to say, well, what's the specific value of c that works? All right, so if y is equal to c times e to the x over 2, then y of 0 would be c e to the 0 square over 2. Now e to the 0 is 1, and so that would be equal to c, which must equal 5, because y of 0 is 5. So, solving the initial value problem, we find that y equals 5 e to the x squared over 2 is the solution of the initial value problem. For what values of r does the function y equals e to the rx satisfy the differential equation y double prime minus 3y prime minus 18y is equal to 0? All right, so we're making an assumption here. We're assuming that a function of the form y equals e to the rx will satisfy the equation. All right, so if, now looking at the differential equation, it involves the derivative and the second derivative. So if y is equal to e to the rx, then y prime would equal e to the rx times r from the chain rule, and y double prime would be equal to e to the rx times r squared. So let's make the assumption that one of these works, right? That some form of y equals e to the rx works. So if we have y double prime minus 3y prime minus 18y is 0, then that becomes e to the rx times r squared minus 3 e to the rx times r minus 18 e to the rx equals 0. Notice that all of these terms have a factor of e to the rx. So I can rewrite this as e to the rx times r squared minus 3r minus 18 is equal to 0. And back from, a beginning algebra course, since I have these factored forms equal to 0, then I can split this up and say e to the rx equals 0, or r squared minus 3r minus 18 equals 0. Now this equation right here, this r squared minus 3r minus 18, we will call the auxiliary equation. I don't expect you to necessarily know that, but that's something that you'll see again in a differential equations course. Now, e to the rx cannot equal 0, right? E to a power is not 0. But r squared minus 3r minus 18 can equal 0, and we can just solve that by factoring. That's r plus 3 by r minus 6 is 0, and so that implies that r is negative 3, or r is 6. So, For what values of r does the function satisfy the differential equation? R equals -3 or r equals 6. And so a conclusion that I could make is, so y equals e to the -3x and y equals e to the 6x are solutions. But in fact, and you'll learn more about this in a differential equations course, we can take this even further. So here's a claim. Y equals c1 e to the -3x plus c2 e to the 6x is a general solution of y double prime minus 3y prime minus 18y equals 0. So notice that that's just what we call a linear combination of those two specific solutions that I listed a few moments ago. All right, so let's verify this claim. All right, so verification. All right, so if y is given by that function, then y prime would be c1 times -3 e to the -3x plus c2 times 6 times e to the 6x. And y double prime would be c1 times 9 e to the -3x plus c2 times 36 e to the 6x. All right, so now let's substitute into the differential equation. Y double prime, c1 by 9 e to the -3x plus c2 by 36 e to the 6x minus 3 times y prime, c1 times -3 e to the -3x plus c2 times 6 e to the 6x minus 18y minus 18 by c1 e to the -3x plus c2 e to the 6x equals 0. That's our claim. All right, so let's see what we got here. Let's go through all the multiplications carefully. So let's see, I've got, 9 c1 e to the -3x plus 36 c2 e to the 6x. Distributive property. Plus 9 c1 e to the -3x minus 18 c2 e to the 6x. Distributing again, minus 18 c1 e to the -3x minus 18 c2 e to the 6x. And this is supposed to be equal to 0. So let's look at the e to the 3x terms. All right, let's focus on the e to the 3x terms, or -3x I should say. The coefficients are 9c1 plus 9c1 minus 18c1, and that's all times e to the -3x. And now let's focus on the e to the 6x terms. See, I'll put a plus. 36c2 minus 18c2 minus 18c2 e to the 6x. 9 plus 9 minus 18, that's 0 e to the -3x. 36 minus 18 plus 0 e to the 6x. So that's certainly equal to 0. So that checks out. And I verified my claim. For what non-zero values of k does y equals sine kt satisfy the differential equation y prime plus 4y equals 0? This would be a good time to pause. Try this one out on your own. All right, so we're making the assumption that y equals sine of kt does satisfy the differential equation. So let's find some derivatives. If y equals sine of kt, then y prime would be the derivative of sine is cosine, so cosine of kt, chain rule times k. Y double prime would be derivative of cosine is negative sine kt, still times the k, and by the chain rule we have another k, so negative sine kt times k squared. So now let's substitute into the differential equation. Y double prime negative sine kt times k squared plus 4y. 4 times y is sine of kt is supposed to be equal to 0. Now let's do some factoring here. I can factor out a sine kt, and I would have left over a negative k squared plus 4 is equal to 0. Now sine kt can equal 0, but that would imply that k is 0. Or negative k squared plus 4 is equal to 0, which implies that k squared is 4, which implies that k is positive or negative 2. So therefore, y equals sine 2t and y equals sine negative 2t are solutions. And in fact, y equals c1 sine 2t plus c2 sine negative 2t is a general solution. So k is positive or negative 2, then y equals sine 2t is a solution. What about that negative 2? Well, if y equals sine of negative 2t, if you remember something from trigonometry, remember that the sine is an odd function, and so remember that the sine of negative x is negative sine x. So this is just the same as negative sine 2t. And in fact, what we'll see later on in a differential equations course is a general solution is some c1 sine of 2t. In fact, any solution of the form y equals c1 sine 2t is a solution. But in fact, we can even go a little further. It turns out that for this differential equation, y equals c1 sine 2t plus c2 cosine 2t is the most general solution. I'll leave it to you as an exercise to verify that that statement is true. Suppose a function y of t satisfies the differential equation dy dt is equal to y to the fourth minus 6y cubed plus 5y squared. And we're asked several questions. What are the constant solutions of the equation? For what values of y is y increasing? And for what values of y is y decreasing? So this is called an autonomous differential equation. It's of the form dy dt is equal to a function of only the y variable. All right, so dy dt is a function of the dependent variable. So what are the constant solutions of the equation? These are sometimes called the equilibrium solutions of the equation. To solve that, we basically notice that dy dt, which is y to the fourth minus 6y cubed plus 5y squared, notice I can do a little bit of factoring here, and I can write that as y squared by y squared minus 6y minus plus 5, excuse me. And so that factors further as y minus 2 by y minus 3. No, it doesn't. It factors as y minus 1 by y minus 5. Sorry about that. So dy dt can be written as y squared by y minus 1 by y minus 5. And so notice, if y equals 0, or y equals 1, or y equals 5, the left-hand side, well, those are all constants, right? If y equals 0, the derivative of 0 is 0, the derivative of 1 is 0, and the derivative of 5 is 0. And if y equals, so the left-hand side is 0, and the right-hand side has to be 0 for any of those values. So these are called the constant or equilibrium solutions. Now, for what values of y is y increasing or decreasing? Well, to show this, I'm going to draw a little sketch here. So here's the y-axis, and I'm going to put, here's y equals 0, here's y equals 1, and here's y equals 5. And basically, I'm going to test some values here. Now, what happens is, at y equals 0, right, if y equals 0, dy dt is 0, and so we get a horizontal line, and basically it's an asymptote. And that's the same thing that happens at 0, 1, and 5. But now what happens in all of those other intervals? Well, let's take a test point. What happens if y is negative 1? If y is negative 1, then y squared is positive, y minus 1 is negative, and y minus 5 is negative. And so this would be positive, which means the dy dt is positive. And so therefore, we must have a function that the y must be increasing. And as it approaches, as the y value approaches that 0 level, it becomes asymptotic. And so we get a curve that does something like this. And so it's increasing. What about if we chose a value between 0 and 1? All right, so if we chose a value between 0 and 1, then the y squared would be positive. The y minus 1, since it's between 0 and 1, y minus 1 would be negative, and the y minus 5 would also be negative, wouldn't it? And so this is also positive, and so it's increasing when y is between 0 and 1. Now it's asymptotic to the left and asymptotic to the right, so we get some kind of curve that looks like this. All right, so I should say, here we are increasing, and this is increasing. All right, what if we chose a value between between 1 and 5? What happens between 1 and 5? Well, 1 squared, some number between 1 and 5 squared would be positive. Let's just say the number is 3. 3 minus 1 would be positive, and 3 minus 5 would be negative. So in between 1 and 5, it's decreasing. It's got to be asymptotic near 5, and asymptotic near 1, but it's decreasing. And finally, if we choose a number for y greater than 5, we have a positive, and a positive. So it must be increasing. And so we get a curve that does something like this. All right, so now later, in a differential equations course, now that we have this sort of diagram, we can now talk about these specific equilibrium solutions, and we can see that they behave differently. And so notice, thinking from left to right, notice how, as we look from left to right, the curves are moving away from y equals 5. And so since they're both moving away, this is called an unstable equilibrium solution. Notice as we look from left to right, the solutions are moving towards y equals 1. And so this would be called a stable solution. And notice that as we move closer to y equals 0, again looking from left to right, sometimes it's moving toward and sometimes it's moving away. This one would be called a semi-stable solution. All right, that concludes this presentation.